Hi everyone and welcome back to PrepFusion. I am Anish and today we will start with the lecture 5 and the final lecture of our resonance chapter. So today we will discuss all the assignment questions that I gave you as homework, right? So first question is this one. A parallel RLC circuit has resonant frequencies 5000 radian per second and bandwidth as 500 radian per second. Calculate the quality factor. So what is quality factor? Simple formula, right? Quality factor is simply equals to omega naught resonant frequency by bandwidth. This is a standard formula. So like this is just a standard formula based question. So resonant frequency is 5000 and bandwidth is 500. So it will be 10. So 10 will be your answer for this particular question, like nothing fancy or something. So this is the next question. We have to find out the resonant frequency of this circuit. Now this is not a standard parallel RLC circuit, neither series nor parallel. So this is neither series nor parallel. Okay, so for these kind of question, right, you can do two things. You find out the Z input impedance, okay, and you make the imaginary of input impedance 0, because I know my circuit behaves as purely resistive when it is at resonance. Or what you can do, you can find out the input admittance and make the admittance to be equal to 0. Both will yield you the same result. Okay, both will give you the same result only. So I am doing impedance here because this one is slightly easier. It is a series element. Admittance will be slightly messy here, so that's why I am choosing impedance. But admittance also you can do. That is the homework for you. You try it with the admittance. I will do it with the impedance. So uh, it is, let's assume it is at the resonant frequency. So how this circuit, right, can be converted in terms of the reactances, correct? So this circuit is here. So it is what? This will provide plus j 0.1 plus j 0.1 omega naught, okay, and this will be 1 by j omega c, right? So c is 1, so this will be 1 by j only, or 1 by j omega naught only, okay, and this is r equals to 1 ohm, okay. So from here I can directly say about my like equivalent. What is the equivalent impedance z dash from here? Then I will just simply add this, right? So ultimately my zn will be equals to this j omega 0.1 omega naught, sorry, j 0.1 omega naught plus z dash. So what is z dash? So z dash is the parallel combination of these two capacitor and the resistor. So it is 1 by j omega naught divided by 1 plus 1 by j omega naught. So this will be my z dash. So if I write this properly, this will be 1 divided by j omega naught plus 1. This will be equals to 1 minus 1 minus j omega naught divided by 1 plus omega naught whole square, okay. So my z in will be equals to I don't care about the okay, I don't care about the real part. Real part will be this 1 plus j omega naught whole square plus j into 0.1 omega naught minus, this is the negative imaginary part, right? So minus omega naught divided by 1 plus omega naught whole square, okay. So ultimately my imaginary part of the input impedance has to be 0 for it to be in resonance, correct? So this will be what? This will be totally 0. This will be totally 0. So my uh, equation becomes 0.1 omega naught minus omega naught divided by 1 plus omega naught whole square, so equal to 0. So I can take omega naught to be common, so this will be 0.1 minus 1 divided by 1 plus omega naught whole square to be common, okay. So there are two things here, either my omega naught is equals to 0 or this whole equation is equals to 0. So of course I will not choose omega naught to be 0. If omega naught is 0, what will happen? If omega naught is 0, this one will be 0, this one will be open circuit, yes. So omega naught equal to 0 is also a valid resonance frequency. But as we are in AC, right, we are discussing about AC quantities, so it is DC, right? Omega naught 0 means it is DC. So we will ignore the DC. We will ignore the DC. So omega naught equal to 0 although it is a solution here, but not valid. Why? Because it is DC. We are not discussing about DC circuits here, we are discussing about AC circuits. So this one we have to equate this one equals to 0. So this will be 0.1 minus 1 divided by 1 plus omega naught whole square equals to 0. So this will be 1 plus omega naught whole square equals to 10, or omega naught whole square equals to 9, or omega naught equals to 3. Okay, so like of course I will ignore the negative solution, like it is plus minus 3, but negative solution not possible, negative solution not possible. Okay, so so 3 radian per second, this will be an answer for the question. Okay, so the resonant frequency will be 3 radian per second. Was it in the options? Okay, yeah, options was there, 3 radian per second. So let's move on to the next question. Next question is very good. I think it was a gate question, but I remember this is a gate question. Okay, so here you have been given a parallel resonance circuit, and they are telling you it is at resonance. They are telling you it is at resonance. So if it is at resonance, they are asking you to select the correct statement. What will be the correct statement? So I observe that they are telling me IR, magnitude of IR will be less than 1 milliampere. Is this correct? No, right? At resonance, I in equals to IR, right? So magnitude of I in will be equals to magnitude of IR will be equals to 1 milliampere as given here, right? It will not be less than 1 milliampere, it will be exactly equals to 1 milliampere. So this option is gone. Magnitude of IR plus IL will be less than 1 milliampere. Now is this true? We have to check. Magnitude of IR plus IC is equal less than 1 milliampere. Is this true? We have to check. Magnitude of IR plus IC is greater than 1 milliampere. All this we have to check, right? So ultimately, what is your I in actually equals to? I in, if I apply the KCL in this node, if I apply the KCL, I in equals to IR plus IL plus IC, the phasor sum. IR plus IL plus IC. So this is what my input current is equals to. Okay, so now what I can say is uh, I do understand this, that my IL at resonance equals to minus JQ I input. I hope you remember this, right? In the previous lecture we discussed about this. And IC is equals to plus JQ into I in basically. Okay, so what I can comment is they are discussing about IR plus IL. So if I do IR plus IL, IR, right? IR is, I have already discussed, IR is equals to I in, correct? So IR plus IL will be equals to, IR is I in plus IL is minus JQ I in. Okay, so this is what I in into 1 minus JQ. Okay, now if I take the magnitude of this whole thing, IR plus IL, this will be equals to magnitude of IN into 1 minus JQ. So this will be equals to magnitude of IN, that is 1, into under root 1 plus q square. Okay, and I know like whatever the value of q, I don't care, q will be something greater than 0, right? And if it is not greater than 0, q square will be q square will be something greater than 0. If it is greater than 0, of course this whole quantity will be something greater than 1. So if it is greater than 1, that means this magnitude is greater than 1 milliampere. So it cannot be less than 1 milliampere. So it cannot be less. Here also, if you do the same observation for IC, I will do the same observation for IC as well. So it is IR plus IC. Again, IR is IN only plus this time it will be plus JQ, but does not matter because we are discussing about magnitude. We are not discussing about phase. So ultimately, right, your magnitude IR plus IC will be equals to IR plus IC will be equals to this, right, I in, this can be written as I in 1 plus JQ. So this will be magnitude of 1 plus JQ. So this will come out to be I in magnitude, that is 1 milliampere, into whole under root 1 plus Q square. Okay, so again, right, same observation that this has to be greater than 1 milliampere because Q square will be greater than Q square will be greater than 0. So if it is greater than 0, so ultimately this will be greater than 1 milliampere. So this option is also wrong. This option is absolutely correct, that IR plus IC magnitude will be greater than 1 milliampere, and it makes sense as well because your IC will take more current than your IR, and if I take the magnitude mod, of course it will be somewhat more than the IN, right? That's why current magnification is happening. Okay, so option D will be the correct answer for this question. So this, right, should be D, not C. This should be D. This was wrong. This should be D. Okay, so that was about it for this question. Let's now solve the next question. So next question is here, where the RMS value of the current I of t will be what? Okay, so whenever a complex circuit will be given, right, whenever complex AC circuit, most of the times you just observe whether it is in resonance or not. So this, right, you have to keep in mind. So in gate exam, they will not ask you very complex circuits from AC because they understand that AC has very huge calculations. So of course they don't like calculations, so they will only give the resonance condition so that the calculation reduces. So let's check, right, what is the input frequency? Input frequency is sine omega naught t, that is 1 radian per second. So if I observe at 1 radian per second, what is the reactance, overall reactance here? So this will be what? This will be XL minus XC, right, plus JXL minus JXC. So plus JXL is omega into L, that is 1, minus JXC is 1 by j omega, that is 1 only. So like plus 1 by j omega. So it is ultimately it is cancelling each other out. So this whole thing, right, this top branch is just short circuit. So it does not matter if a 1 ohm is there. If I have short circuited it, it does not matter, right? If a 1 ohm is there, it will just simply short circuit it. The voltage drop will be 0 across this 1 ohm. So ultimately the circuit gets reduced to this whole thing. Okay, very simple circuit. It becomes very simple circuit. One ohm. This is sine t, and they are asking this I of t, right? They are asking what? They are asking the RMS value of I of t. So what is the current? I of t is what? This voltage by current, voltage by resistance. So sine t divided by 1 ohm. So it is sine t only. And what is the RMS value of sine t? RMS value is 1 by root 2. Right? RMS is root 2 times the peak. So it will be 1 by root 2. Peak value is 1 amperes. Root 2 divided by the peak will be the RMS, that is 1 by root 2. So option B will be the correct answer of this question. Okay, option B will be the correct answer of this question. Very simple and easy question to solve. So like just keep this in mind whenever you have something like this, right? If I have this is very useful in interviews as well. This plus z and minus z is there, right? Some minus z plus z. So ultimately, right, it does not matter whatever is in parallel with this. Some r, some, like, they will confuse you. They will have r here, they will have c here, they will have l here. It does not matter, right? Whatever is in parallel, ultimately, right, this whole thing is equivalent to a short circuit. Does not matter. Whole thing is equivalent to a short circuit. Another thing, that let's say if something like this is written, right? If here I have plus z, here I have minus z, and let's say here I have a resistor, and here I am applying some current. Okay, some current is there. So these two, right, will just behave as open circuit. Why? If I just find out the equivalent impedance provided by these two, it will be plus z into minus z divided by plus z minus z. So the denominator is 0, so it is tending towards infinity. It is tending towards infinity. That's it. Okay, denominator is 0, so it is tending towards infinity. So this will be these two will be behaving as open circuit. So ultimately my circuit, right, will be reduced to this. Okay, so these two things you should keep in mind. So let's now solve the next question. So in the next question, we have been given a series LCR circuit. So it is a series RLC circuit operated at a frequency different from resonant frequency. So it is not operating at resonant frequency. The operating frequency is such that the current leads the supply voltage. That means it is behaving as capacitive, because current leads the supply voltage. That means overall it is behaving as capacitive. And in a series RLC circuit, when do my circuit behaves as capacitive? When my omega naught is when my omega is less than omega naught. Okay, the magnitude of the current is half the value at resonance. So at this frequency, I magnitude at omega equals to some omega x is half the peak current. That is, let me write this as Im by 2. Assume the peak current is Im. If the values of LRC are all 1 farad, so what is my omega naught? Omega naught will be 1 by under root LC. So 1 by 1 into 1 under root 1. So it will be 1 only. Okay, and what is the bandwidth? Bandwidth is R by L. So it will be 1 radian per second only. Okay, the operating angular frequency. What is the operating angular frequency? If this is half, so at resonance, it is a, first of all, it is a series RLC circuit, right? So a series RLC circuit will be something like this. RLC. Okay, this is my voltage basically, and this is my frequency omega x. So at when the current is peak, right, at resonance, magnitude of I is what at resonance? It is simply equals to Vm, the peak current, divided by R, because it behaves as a purely resistive circuit. What is the magnitude of the current at omega equals to omega x? It will be Vm divided by under root R square plus XL minus XC, or I can write this omega x into L. Omega no, L is 1, so minus 1 by omega x. Okay, so this is equals to basically my current. This is equals to Vm by 2R, because they have told me it is half the resonant current. So ultimately Vm will get cancelled. So this will become, if I square both sides, this will be 4R square will be equals to R square. This is plus omega x minus 1 by omega x. So omega x whole square minus 1 is equals to okay, this is 3r, right? Omega x, okay, r is already 1, right? R is also 1, right? So okay, r is 1, so this will be 3 only. This will be 3 omega x. Okay, so from here I can literally write omega x whole square minus 3 omega x minus 1 equals to 0. So omega x will be equals to minus b, that is 3 plus minus b square minus 4ac divided by 2a. So from here if I write the values, this will be 13 under root, and of course I will not choose the negative value because negative frequency obviously is not possible, so I will only choose the positive value. Okay, this is omega x square omega whole square. If I do, yeah, this is fine. Yeah, so if I choose the positive value, this will be plus 3 divided by 2, so this will be 3.3. okay, so 3.3 will be your answer for this question. I will just quickly check whether I am doing anything wrong here or not. So this is under root r vm by r. Okay, r square is 1 only. Okay, if I square this, okay, sorry, so I made a huge error. This is squared, right? This is squared. So if this is squared, this will be under root 3 actually. Sorry, this, right, will be actually here, right? I should have written this will be omega x square minus 1 by omega x whole square equals to 3. So your omega, like I was making a mistake because I know the answer I was not getting correct. So you just be careful with all these mistakes, right? 1 by, now this, right, can be plus minus under root 3 omega x. So shall I choose the plus or the negative? So here, right, very interesting thing comes up. Here very interesting thing comes up, that omega x, what is my omega naught? If I choose this negative, here you cannot conclusively say, so we will discuss, right? Here I am getting two solutions, plus minus under root omega x. Okay, so let us solve. So let's first solve for the plus omega plus under root 3 omega x. So this will, the equation will become under root 3 omega x, okay, minus 1. So ultimately this will be b minus b plus minus b square minus 4ac. Okay, so this is minus b, right? Minus b will be minus only. Okay, no, this negative goes on that side. Let me choose the plus under root 3. If I choose the plus under root 3, negative will go that. Okay, this will be plus b only. Okay, so this will be under root 3 plus under root 7 divided by 2. Okay, so if I choose this one, basically, right, from here also you can like nullify. Like, what do I mean? So I will just show one thing. Okay, one thing I will show, just hold on. So here, right, let me not simplify this, let me keep it as it is. Okay, just to explain you one thing, I just want to explain you one thing. So this is omega x by 2. Now if I take the under root, right, if I take the under root, this will be omega x by 1 by omega x equals to plus minus under root 3. Now which one will you choose? So I know my circuit is capacitive. If my circuit is capacitive, this one will be dominating than this one, right? It is the omega L component and this is the 1 by omega C component. Circuit is capacitive, so this one will be dominating, XC will be dominating than XL. XC will be higher than XL. So basically my 1 by omega x will be higher than omega x into, like, L and C both are 1. So 1 by omega x will be higher than omega x. So of course if this is higher, I am subtracting more, so I will choose the negative solution. I will ignore the positive solution. That's why the gate examiner has given you this data. So trust me, whatever data they give, right, they give accurate data. So that's why the circuit will behave as purely capacitive. Not purely capacitive, sorry, circuit will behave as capacitive. That's why I will choose negative value. Okay, I will choose the negative value. So this, if I choose the negative, on the right hand side, if it goes, this will be plus. Okay, and if I multiply omega x, this will be plus omega x minus 1, this will be minus root 3 plus minus root 7. So root 3, then of course I cannot choose negative, because if I choose this as negative, right, then of course I will get a negative frequency, which is not possible. I will choose the positive value. So plus root 7 divided by 2, so it is 0.45457 radian per second, 0. Okay, so this will be the answer of this question. So like just keep in mind, of course I am ignoring the negative solution, ignoring negative solution, because omega x has to be positive. I am we only discussing about the positive frequencies. Now let's solve this next question. This question is very interesting, so you can try this question out by yourself. You can pause the video and try it out by yourself. Okay, so here we have a, like, this structure, right? This structure is actually known as a tank circuit. Okay, so this is a type of a special, like, this structure. I will just copy this, copy this. This structure is known as a special tank circuit. Okay, so what we can discuss is, like, there is a special condition that is what we will discuss basically. So the question is asking, determine the value of R in the given circuit to achieve resonance at all frequencies. So they're telling me, I don't care what is the frequency, at all frequencies the circuit will be in resonance. So there are many ways to go about this problem. This is a very beautiful problem. So first, method 1 is using the phasor diagram. Okay, using the phasor diagram. So what happens at resonance? The supply voltage and the supply current are in the same phase, because the circuit behaves as purely resistive circuit. That is what happens at resonance. Correct? So this is I1, this is I2. Okay, so now let's discuss, right? So this voltage is parallel across both of them. So what I can do, I can assume my voltage to be reference, because this is neither series, neither parallel. Okay, because all the elements are neither in series or parallel, but I am observing that this voltage is across this whole circuit, this voltage is same across this whole circuit only. So let me assume the voltage to be parallel, because this current is getting divided between the two. So my easier thing would be to assume the voltage to be the reference. So this is my V in, that is reference basically, that is reference. Okay, so now next thing is that, what about the currents? So my I in is equals to I1 plus I2, phasor sum of I1 and I2. So voltage is angle V in, assume it as reference. So V in is some magnitude of V in, angle 0. Okay, what about the current I1? What will be the phase of current I1? So I1 is flowing across a RL circuit, and what happens in a RL circuit, the current lags the voltage. Voltage is V in, so current will lag the voltage. So it will be some magnitude of I1 into minus of theta, something like that. Okay, because it is lagging, right? It will lag, current lags the voltage for a RL circuit, so it will be negative. So it will be somewhat in the clockwise direction. So I1 will be somewhere here. Okay, so yeah, this is the minus theta 1, whatever the value is. Okay, minus theta 1. Okay, let me assume this is minus theta 1, and of course theta 1 is positive, right? I have assumed theta 1 to be positive, that's why I am writing here minus sign to specify it is negative angle. And your I2 is flowing across a RC circuit, so it is a leading circuit. So here current will lead the voltage. Voltage is what? V in, same voltage only. So current will lead the voltage. So your I2 will be magnitude of I2 angle of plus theta 2. So I2 will be somewhere here. Okay, plus theta 2. Okay, this is my I2 basically. So now interesting fact is, what is ion? Ion is the combination of these two, right? Sum of these two. But I know as it is in resonance, I don't care about frequency, whatever frequency, ion should be magnitude of ion plus theta 2. Okay, ion should be magnitude of ion plus theta 2. So now, sorry, not theta 2, sorry, 0, right? Because it is in the same phase, because circuit is in resonance, so current and voltage will not have any phase difference. Current and voltage will not have any phase difference. So ion will also be lying here only. Ion will also be lying here only. Okay, so important point to note is this I2, right, will have two components. One will be in the y axis, one will be along the V in, right? So this I2 I can break into components here. Okay, I'm just explaining the question. I'm not actually solving it. Okay, so if I would have solved it, I would have solved it much faster. But as I am explaining you, so I am going very slow. Okay, everything I am explaining. So this I2 will have two components. One component will be here, that is I2 sine phi 2 theta 2, and this I2 will have another component here on along the V in, that is this component will be I2 cos theta 2. Okay, so yeah, that is the case. And this I1 can also be broken down, right? This I1 can be broken down into two things, that is I1 sin theta 1, and here it will be I1 cos theta 1. Okay, so yeah, that is the case over here. Now what is the important point is that as my in will be in phase, and in is the combination of I2 and I1, so of course this has to cancel each other out. If this doesn't cancel each other out, that means my in will have some phase angle either here or here, right? That is not possible. Of course the y component has to cancel each other out, that is all of the components should be in the x direction only. Okay, that is the assumption, correct? So your in is equals to I1 plus I2, correct? So first equation what I get is these two must be same. These two must be same, right? So basically magnitude of I1 sine theta 1 must be equals to magnitude of I2 sine theta 2. Okay. So now what are the next points? Next point is my circuit will be purely resistive, right? I will not be able to see it as voltage. My circuit will be purely resistive. Okay, so can I do anything else? So mm, okay, 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 I'm just thinking, can I do anything else? mm, all frequencies, it will be resonance. So these are the values in. Okay, so in is this in. So what is my in equals to? In is equals to basically the addition of these two vectors, right? This I2 cos theta 2 and this I1 cos theta 1. So I will write that. So in, magnitude of in, or like anyways in is in the zero phase only, that is I1 in is equals to I1 cos theta 1 plus I2 cos theta 2. Okay, this is my in value, magnitude of I1, magnitude of I2. Now one more thing I know, that what is this cos theta 1 and theta 2? Can I find out this cos theta 1 and theta 2? Yes, there is a solution to this cos theta 1 theta 2. So basically I1 is the current across this series RL circuit, right, where the voltage is V in. So if I just individually draw the phasor diagram of, let's say, the RL circuit, so this is my voltage V in across the RL circuit, and the current, right, will lag basically. Current will lag. So by how much it will lag? By how much it will lag? So this is my current I1, right? So how can I identify the lag of the current will be determined by this RNL, by the impedance angle, because impedance angle and the angle between voltage and current are same, correct? So if I find out phi z somehow, phi z1, that will be equals to my theta 1 only. So what is theta z1? Theta z1 is, if I draw the impedance triangle, so impedance triangle is here, R is here in the reference, and XL will lead plus JXL, right? So XL will lead here, and this will be basically my impedance triangle. Ultimately this will be my impedance triangle, correct? So this is my equivalent Z1, and this is my theta 1 basically. So theta 1 will be basically equals to tan inverse XL by R. This we have already discussed how it comes. All these things have been discussed in phasor diagram, so I am not explaining here. Okay, but I don't even need theta 1, right? What I need is, I just need this sine theta 1. Somehow if I am able to find this sine theta 1, okay, sine theta 1 and cos theta 1, sorry, sine theta 1 and cos theta 1. So what is sine theta 1? Sine theta 1, sine theta 1 will be what? It is the opposite upon the hypotenuse. So opposite is opposite as R, and hypotenuse is Z, magnitude of Z1, right? R1 by Z1, or this is R only, same resistance is there, right? So it is R by magnitude of Z1. Okay, same for sine theta 2 as well, same for sine theta 2, same impedance triangle you will draw. So it will be coming as R by, sorry, this is not R, sorry, this is the opposite, right? Opposite is the XL, right? This what is the XL, right? This is the XL, right? Sorry, I'm really sorry. So this will be XL by Z1, this will be XL by magnitude of Z1. Okay, so we get this sine theta 1 and sine theta 2. Okay, so I have got this value. Now what I can do is, I can replace this sine theta 1 and sine theta 2 here. Okay, so it will be sorry, this is Z, not Z1, sorry, this is Z2. So basically, right, I will replace this sine theta 1 and sine theta 2 here, right? Okay, and what is my I1 and I2? Magnitude of I1 and I2. So magnitude of I1, if I say what is the magnitude of I1? Magnitude of I1 will be the voltage upon the impedance, correct? Voltage upon the impedance. So magnitude of I1 equals to voltage V in, magnitude of voltage upon the magnitude of the impedance, and magnitude of I2 is the magnitude of the voltage Vn divided by magnitude of Z2. Okay, so now what you have to do is you have to replace everything in this equation. That's it. So this will be magnitude of Vn, divided by magnitude of Z1 into this is magnitude of this is XL divided by magnitude of Z1. Okay, the sine theta one, and this will be magnitude of Vn divided by Xc Z2. Okay, so now if I do this, like V in magnitude of V in is same, right? It will get cancelled. So what is XL? XL is sum omega into L, correct? And this is Z1 whole square. What is magnitude of Z1? Magnitude of Z1 is simply the impedance, right? Magnitude of the impedance, that is R square. It is series RL circuit, so R square plus omega L whole square. And what is magnitude of Z2? It is series RC circuit, so it will be R square plus 1 by omega C whole square. Okay, so this will be yeah, omega L divided by this is magnitude of Z1 square, so this under root will go away, so this will be only R square plus omega L whole square equals to, this will be 1 by omega C divided by R square plus 1 by omega C whole square. Okay, so now very interesting things will happen. Okay, very interesting things will happen. So I hope you are working with me. Okay, so here basically I will just rearrange the terms. This will be omega square LC equals to R square plus omega L whole square divided by R square plus 1 by omega C whole square. So omega square is equals to, so like what I can do, I can rearrange this. This will be omega square and LC is here into R square. I can multiply omega, right? So yeah, that is what we can do. This will be omega C whole square into R square. Omega C whole square into R square plus 1. Okay, omega C R square whole square into 1. Okay, fine. And also okay, just hold on, I will just rearrange this properly. If I multiply by omega C whole square on both sides, this will be omega C whole square. Okay, this is here R square plus omega L whole square divided by R omega C whole square plus 1. So right, what is happening, omega square and omega square can cancel, one of the C, like this C can cancel, right? So this will be here L by C. Assumption is omega is not equal to 0, then only I can cancel this. If omega is 0, I cannot divide by omega, right? I cannot do it. Okay, so that's why this is L by C. Basically here, right, omega square gets cancelled, C square and C gets cancelled, so this will be L by C, and then again I will multiply here R omega C whole square plus 1 on the right hand side I will have r square plus omega L whole square. Now what I will do, right, I will just try to take the omega square terms together, because I have to make this somehow frequency independent, right, because they have told me for all frequencies it has to satisfy, for all frequencies it has to satisfy. So let me just take the like terms together. So this will be omega square, if I take this on the right hand side, right, L by C is there, right, so omega square if I take it common, so here this is C, so this will be omega square r square C LC, omega square r square LC, so this will be L square minus r square LC. Okay, r square LC, omega square r square LC. Okay, so and this will be here, what will be this value, what will be the other constant term? Other constant term is simply r square minus L by C. Okay, so what I have to do is I have to make this frequency independent. I have to make this term frequency independent, like for any value of omega this should always satisfy, because that is what they have asked, right. So what is this condition? Basically this condition came from this one, right, this condition came from this condition, and from where this condition came? This condition came from here, right. From where this condition came? This condition came from the question that they, in the question they have told me that at all frequencies it should be in resonance. Resonance meaning there should not be any imaginary component of current, all of the components should be in phase with the voltage. So ultimately somehow I have to satisfy this equation, and they have told me that omega can be any value. So if omega is any value, that means I have to make this equation 0. So like I have to make this, because here, right, my L is positive, L, C and R, all these are positive quantities, right, these are passive networks, all these are positive quantities. So these are positive quantities, and I'm adding these things, this is something positive, right. So individually they have to be 0. If individually these are 0, then obviously the right hand side and left hand side will be satisfying. So individually if I make it 0, it is saying L square minus R square LC has to be equal to 0. That is R has to be equals to R square has to be equals to L by C, or R is equals to under root L by C. Okay, does it make sense? You can do a quick sanity check. You can check the units. So if I check the units, what am I getting? If I check the units, what I am observing is that it's ohm, right. I have already told you the unit of under root L by C is ohm, because it is a characteristics impedance. So this is a special impedance that of course we will discuss in power systems. We will not discuss now, we will discuss in power systems. But okay, the equation 1 is telling this. Let's see the equation 2. Equation 2 also is telling the same thing only, that is R equals to under root L by C. So of course it is satisfying. For a single value of R only, this will be always 0, that is R equals to under root L by C. So this will be your answer for the question. Okay, if in the question they have asked for all frequencies it has to be in resonance, so this is the answer. Okay, now there is a other way to solve this as well. There is a other way to solve this as well. What is the other way? Other way is like, it is just like a bit intuition. So if you did not understand it, that is totally fine. That is totally fine if you are not able to understand the method 2. Okay, so this was the phasor method, or like method 3 is there. Method 3 is what? Simply you do what? You find the Zin, okay, then you make the imaginary part of Zin to be 0, like without using any brains, right, just make the imaginary part of Zin to be 0, and from there you will get a condition, and with the help of condition, like same condition you will get, same equation you will get, you will get the value of R. Okay, so this is the method 2, that is with the help of impedance. And admittance also, like you can do whichever one is suitable to you, either impedance or admittance. Okay, what is the third method? Third method is a bit intuitive method. So in the third method, okay, in the third method what you will do is, I have this circuit, right. So I can assume it as a Wheatstone bridge. Why can I assume it as a Wheatstone bridge? Why can I assume it as a Wheatstone bridge? Because what I can comment is this I in is equals to I1 plus I2, correct? I in is equals to I1 plus I2. Yeah, so I was basically thinking about something like basically what happens, right? This I have taught previously as well. Basically, uh, the thing is it behaves as a bridge circuit, right? This is more like a bridge circuit. So what happens? This point is at the same potential. Okay. So if we apply the Laplace condition, that is a bridge condition, the Laplace impedance of this is SL into the opposite side impedance, that is 1 by SC, okay, into the opposite side impedance 1 by SC equals to these two multiplication, right? If the bridge is balanced, here the bridge is balanced, then only it will be totally real circuit. Okay, so from here R into R, your basically S is what? S gets cancelled, so your R square is equals to L by C, and your R is equals to under root L by C. So we get the same result, but problem is like I am not able to prove, right, why is that this the case. Like I was in this thing for like 1 hour, okay, I was thinking really hard, but somehow like this I have taught previously as well, but I'm not able to prove, right, that how is it the case. So this is a special case basically where it behaves as a bridge circuit. So uh, I'm giving you the homework task, like if you can, if you are really interested, right, can you just try to identify why is this happening, this bridge balance, right? I was trying to look for it, I was trying to search nowhere. You will find this nowhere, this technique you will find nowhere. Okay, I was thinking you can draw the phasor diagram, so you can write the currents. So basically, right, this point and this point will be in the same potential. So yeah, that you can try it out, because I have to teach the other things as well, so I have to move on. Basically the same question only, but in this question we have to find out the value of omega naught for the given circuit. Okay, so resistor is fixed now, resistor value is fixed. Okay, now I am varying my omega naught. So now I will use the method to basically impedance you will try, I will try with admittance. Okay, so my y input admittance equals to what? Input admittance, like I will make the imaginary part of the admittance to be 0, so then only it will be in the resonance. So the y input admittance is this, because these two individual circuits are in parallel, so this will be y RL, okay, plus y RC. Okay, so what is YRL? Basically YRL will be what? It will be 1 upon R plus JXL, and YRC will be 1 upon R minus JXC. Okay, so this value will be Y in equals to R minus JXC plus R plus JXL okay, R minus JXC. So here I will just write the real and imaginary parts. This is very typical. So okay, things are changing a bit. I have to do so, like I don't think we should, yeah, we should not directly add this. So this is not the right way to add, right? So first I will convert this into real and imaginary, that will be the better part. So right, this I will rationalize. So this will be R minus JXL, okay, divided by R square plus XL square plus R plus JXC divided by R square plus XC square. So from here, right, the imaginary part will be 0. The imaginary of Y in shall be 0 for it to be in resonance. So basically this is the real portion, right? I don't care about the real portion, I care about the imaginary portion. So basically this xl by r square plus xl whole square will be equals to xc by r square plus xc square. So now I'm observing, like maybe you may feel like phasor is the difficult one, but like that is also a beautiful solution sometimes, right? That will be easier one, because there you have to think more. Here you don't have to think, it is just like a simple programming, right? Just you make this y input, imaginary part of the input, add bit as 0, and that's it. Okay, there you have to think a bit, put a bit of pressure in brain. But trust me, in gate examination, right, calculative questions will be there, but more brainstorming questions will be there. So you have to think out of the box as well sometimes. So try to understand all the methods. Okay, don't just try to see, okay, I know this method, I am solving this method, and that's it. No, try to understand all the methods. You never know when that method will be useful in the examination hall. Okay, you never know. So from here, xl is what? Xl is omega naught l, because I have to find out the resonant frequency. Now my r is not varying, r is fixed. So this is r square plus omega l whole square, and this will be 1 by omega naught c divided by r square plus 1 by omega naught c whole square. Okay, so this will be omega naught whole square. This will be equals to omega naught whole square. This will be equals to 1 by lc. Okay, and yeah, this is on this side, right? Okay, before that, right, let me just multiply by this coefficient, this denominator. So if I multiply omega naught c whole square on both sides, this will be omega naught l equals to omega naught c divided by r omega naught c whole square plus 1. Okay, so this will be L by C, like I will get the same condition, right? I will get the same condition. This will be R omega naught C whole square equals to C by L. This is plus 1. So ultimately, right, anywhere I have done something wrong. Somewhere I may have done something. Okay, here, right? Still I have this R square omega L. So this is still there, right? Okay, this will go there. Okay, this I forgot that in the denominator I have this term, right, r square omega naught l whole square. So this will be basically c by l and multiplied by r square plus omega naught l whole square. So ultimately this will be 1 plus r omega naught c whole square equals to c by l r square plus c by l and omega naught l whole square. Okay, so ultimately, right, you have to club the omega naught term together. Omega naught square, if I take it together, it will be c l minus r square c square. Okay, this plus here I have on this side, this is 1 okay, no, r square c by l minus 1. Okay, so somehow, right, I want this to be independent of r, because I don't want a condition on r. So what I will do, I will try to make this, right. So for to make this, what I have to do, I have to take common c and I have to take common lc. So I have to basically take common lc from here. So this will be omega naught square. If I take lc common, this will be 1 minus r square c and this will be minus 1 by L. Okay, so basically, right, I can cancel this one out. I can cancel because this is r square is constant, and I will cancel this one out only if what, only if my, okay, can I cancel? No, I cannot simply cancel this one out because this is different, right? Okay, this is negative. Okay, this is negative. I'm just checking whether I can simply cancel. Okay, yeah, I can simply, for now I can cancel because RL is equals to RC. Yeah, RL is equals to RC. Okay, one minute mistake we have done is actually, right, the question had a bit of different thing. I'm really sorry in the question because I'm just like I'm verifying the answers. Actually, I'm really sorry. This will be RL, okay, and this will be RC. I'm really sorry. Please comment section पे मारना मत मुझे, ठीक है, मारना मत comment section पे. तो this will be RL and RC. Okay, so please forgive me. Basically, right, if RL equals to RC, then your resonant frequency will be 1 by LC. Okay, I will prove it to you. So few modifications we have to do. So this, right, this will be RL, this will be RC, this will be RL, this will be RC, RL, RC, okay, RL, RC, great. This will be RL, this will be RC, okay, this will be RL, RC, RC, RL, okay, RC, RL, okay. So from here, right, the changes will happen basically. So this will be again this omega naught CL is there, so this will go on now. Okay, this has gone this side, and this has, okay, something I have messed up, right? Okay, both are wrong actually. This is not the correct way to write. I have done it wrong basically, written it wrong. So this will be, if this term comes here, so this will be RC square into C square minus C C by L, no, not C, minus LC basically. Omega naught square will also be in common. This will be C by L RL whole square minus 1. Now the interesting fact will happen basically. So what I can do, right, I can take this C by L common, okay, to rearrange this. I can take this C by L common. So previously, right, the answer will be 1 by under LC in the, if RL equals to RC, that I will prove it to you here. So your omega naught, if I just take this C by L common, right, from here if I take this C by L common, and from here if I take C square common, okay, so I will take common C square here, omega naught square RC whole square minus L by C equals to, if I take this C by L common, okay, RL square minus C by L, this will be L by C basically. Now, right, this C and C will get cancelled. So ultimately your omega naught will be equals to 1 by under root LC whole under root RL square minus L by C divided by RC square minus L by C. So this is a very important result, and I really say you to remember things, but this one, right, you can memorize because this is a very like not standard circuit, but this circuit, right, can be modified. Okay, let's say if this was 0, then can you tell me the resonant frequency? What you will do? You will just put here RL equals to 0, right? Here you will put RL equal to 0. Everything else will remain same. Everything else will remain same. Okay. So this will be RC square, right? Let's say this resistor is not there. It is 0. So again you can find out the resonant frequency for the modified circuit. Just put RC equal to 0 in this formula. Okay. So this, right, is a very important one, and how to remember I will tell you. First one is this 1 by under root LC. This is easily remembered, right? This you can easily remember. So next point is, if your RL is equals to RC equals to R, So basically this and this will get cancelled, so it will be under root 1. So ultimately your omega naught is equals to 1 by under root LC. It's the same only, right? It does not change. So which I have already told you that it will be that case if RL is equals to RC. But if RL is not equal to RC and the circuit is something like this, how will you remember? So first this part is sorted, right? This will be 1 by under root LC, this part is sorted. This you can easily remember. Okay, what about the other part? So for the other part, what you do is you basically uh, calculate, you basically calculate what? You basically write, first you have to remember in the top RL will come, in the bottom RC will come. Why? Because I have told you the characteristics impedance generally is L by C. Okay, so you remember it like this, in the top RL will come, in the bottom RC will come, like this you remember. Okay, in the top due to this L, RL will come, in the bottom RC will come. You write, okay, RL, will it be squared or will it be not squared? So this L by C, right? What is the unit of L by C? I have told you under root L by C is characteristic impedance and the unit of under root L by C is ohms. So if I square on both sides, what will be the unit of L by C? It will be ohm square. So as I have ohm square here, that means definitely I have to square RL as well. So that's why, because both of them have to have same units, right? Then only I can add or subtract two quantities if they have the same units. So this will be RL square minus L by C. This will be RC square minus L by C. Okay, so that's why the square will be there. How L will be at the top, how C will be at the bottom. I hope you have understood. I hope now you can easily identify, like I will give you homeworks and please try to solve by yourself. Basically, right, you can easily identify the modified circuits. So let me make this 0 once. Okay, then let me make this 0, but of course there needs to be at least one L and C. Okay, that's the only condition, except that there is no other condition. So you can easily find out the resonant frequency for these two circuits. Just in this equation, in this circuit, put RL equals to 0 because it is 0 resistance. In this circuit, put RC equal to 0. Okay, and you will find out your resonant frequency. You cross verify with actual method what I have told you, with the imaginary part of the impedance admittance to be 0 and with this formula as well. Okay, very rarely I tell you to remember the formula, but this time I am telling you to remember the formula because it will be very helpful for you. Okay, so one more question is there, that for this circuit, for this same circuit to always work in resonance, what shall be the condition of R, L and RC? So if this circuit, for this circuit to be always at resonance, what shall be the condition of RL and RC? Okay, so basically, right, what you have to do is you have to again go with the balance bridge condition, and I don't have proof currently why it works. I have to figure it out. But if you go by the balance bridge condition, right, basically it will be RL into RC, balance bridge, right? So opposite impedances are multiplied. So basically L by C is equals to RL into RC. So this is the condition that needs to get satisfied if you want uh, your circuit to always operate at resonance. And trust me, right, these questions, right, no one will take, no other educator, no one in this gate field very rarely will take this kind of question, right? And I have intuitively tried to explain as well. Okay, so currently I don't have the proof, I have to figure out the proof, but like this thing, few things you can keep in mind. Okay, intuition you can keep in mind. So this will always work. You can go again use the same method, right, that phasor diagram, and through that also you will see this is the condition that you are getting. You can use the phasor diagram and verify phasor diagram method. Okay, with the phasor diagram method, if you verify, you can basically confirm this one, right? You can confirm the values, you can confirm that whether this condition is matching or not. Okay, that you confirm, that is the homework for you. Okay, so I hope like we are almost there. Okay, we are not almost there, still few things are left. Okay, okay, so this is the general procedure to determine the resonant frequency for non-standard circuit. So standard circuit I have already discussed, parallel RLC and series RLC. For non-standard we have done, right? Simply what do? You calculate the equivalent impedance or admittance and you make the imaginary part 0. Okay, then you apply the resonant condition, that is imaginary part 0, and then you solve for omega naught. So that was the basic, very basic method. Okay, so now another very good question that came in GATE. Okay, this is a very great question that came in GATE. So here we have a symmetrical square waveform of 50% duty cycle. Like, trust me, this question no educator in network theory will take. Okay, and no educator in power electronics will take. Okay, power electronics guy will say this is the network theory question, and network theory guy will say, network theory teacher educator will say that this is the question for power electronics. Okay, no one will take this question. So we have a symmetrical square waveform with duty cycle 50%. So duty cycle 50% means for 50% of the time it is on, and for 50% of the time it is off. So that is what 50% duty cycle means. For 50% duty cycle, that is T by 2, it is on, and for other T by 2 it is off. Okay, or vice versa. So it is plus minus 15 volts. Okay, so it is varying between plus minus 15 volts. Maximum value is plus 15, minimum value is minus 15. Okay, and time period of 0.4 pi. So it has a time period of 0.4 pi. So time period meaning the whole repetition, right? So this is 0.4 pi. Okay, the milliseconds. So this is in 0.4 pi milliseconds. So I will write the things here. T is 0.4 pi milliseconds. Can you find out the frequency? So we know, right? We know T is equals to 2 pi by omega. So the frequency omega will be equals to what? Omega will be, this will be go on there, this is 5, pi will get cancelled, this is 5 into so 5. Okay, so yeah, omega is there. Yeah, that is the case here. And omega is this value, right? So now it is a series RLC circuit. RLC are given. The amplitude of the 5000 radian second component of the capacitor voltage will be equals to what? What will be the amplitude of the 5000 radian per second component? Okay, that is what they are asking basically. That is what they are asking. Okay, so you know that let me check resonant condition, because this is the resonance chapter, and I have always told you that whenever some very weird question, AC question will come, right, always try to check the resonant condition whether the circuit is in resonance or not. So if you check the resonant condition for a simple series RLC circuit, what is the resonant frequency? 1 by under root LC. So it is equals to 1 by under root LC. Okay, L is 10 millihenry, C is 4 microfarad. So this will be basically okay, just hold on, let me just check one thing. Yeah, this will be basically, this is 2, right? So this is 1 by 2 into 10 raised to power minus 2 10 raised to minus 8. So this will be 10 raised to power 4. So this is 5000 radian per second. So actually I am very lucky, right? So whatever frequency they have given me of the waveform, that is equals to my omega naught. The input frequency omega in and omega naught are same. omega in and omega naught are same. Okay, so you will say circuit is in resonance. So what have they asked? They have asked the amplitude of the voltage across the capacitor. So you know, if the circuit is in resonance, you directly say the magnitude of the voltage across the capacitor is Q into magnitude of the input voltage, the peak voltage, right? So it will be, what is Q? Q is either you can remember the formula 1 by R under root L by C, or you can directly write omega naught by bandwidth, whichever one is suitable to you. So under root L by C. So what is 1 by R? R is 5 ohms. Okay, R is 5 ohms. And L is 10 millihenry by 4 microfarad. Okay, so Q will be equals to 1 by 5 under root, this will be 10 raised to power 6, 10 raised to power 3, 10 raised to power 3, 10 raised to power 4, 250. Okay, 10 raised to power 4 is there, right? So this will be, so this will be 100 divided by 2. So this will be 100 divided by 2. So this will be 10 basically. So quality factor is 10. Okay, so if quality factor is 10, what you will do, you will just directly say that your magnitude of Vc will be equals to 10 times the maximum value of V in, that is 15. So it will be 150 volts, and you will be very wrong. Okay, because you haven't yet studied signals. Okay, and what have I told you? This formula is only valid when the input is sinusoidal. When the input is sinusoidal, only then this formula will be valid. Was your input sinusoidal? Was it sinusoidal? No, it wasn't. It was not sinusoidal. So problem is, you don't know then what is this input, because we have never solved for this kind of input, right? Never solved for this kind of input. So in the chapter of signals, you will study about this. Don't worry if you don't know this. Just trust my word right now, whatever I am speaking. So a square waveform, a square wave with 50% duty cycle. Just trust me, you will study this in signals. You have to trust me right now. Okay, and your signals educator will not teach this question, right? Because it is, obviously it is not a signals, right? Totally signals, but you will need the signals concept here. So this was a very good question, and this is a gate PYQ. This is not even like any random question, right? This is a gate PYQ. So yeah, just be careful regarding that. So a square wave 50% with 50% duty cycle can be written in terms of sinusoid. Can be written in terms of sinusoid. Okay, so your input Vi of t will be equals to basically 4, just trust me here, it is actually equals to 2 into peak to peak amplitude divided by n pi. Okay, where n is varying from 1, 3, 5. It is the odd harmonics to infinity. It will go to infinity. Basically, right, you can divide your square waveform in multiple summation of sine waves. Okay, this you will learn in signals. How you can do it, Fourier transform and all those things you will learn in signals. Just you have to use this formula. It is equals to sine n omega t. Okay, where omega is the frequency, basically 2 pi by t, and like there are many harmonics. So omega in our case is 5000 radian per second. So let's revisit the question again. So what have they asked? Basically, right, the input is a combination of multiple sine waves. Input is a combination of multiple sine waves. What have they asked? They have asked me the amplitude of the 5000 radian component. So you should have taken the hint here. They are asking me the amplitude of the 5000 radian component, because they also know that your square waveform, right, is not totally a sinusoid. So it will have many sinusoids which are added together, which have the frequency multiple to or odd multiple of the fundamental frequency. Fundamental frequency is the frequency of the square waveform. This you will learn in the signals and system. So basically you can write 2 into peak, right? Basically if your peak, like if your waveform is somewhat like this, if your waveform is somewhat like this, plus minus Vm plus Vm minus Vm, okay. So 2 into peak to peak, what is the peak to peak distance? 2 Vm, right? Peak to peak distance is the 2 Vm. So this will be 2 Vm, and of course I have to multiply extra 2 divide by n pi summation n equals to 1 3 5 to infinity sine n omega t, okay. So this, right, can be written like this: 4 Vm by pi sine omega t plus 4 Vm by 3 pi. Basically, right, the amplitude of the sinusoid will reduce as I go into the high frequency. So this will be sine 3 omega t and so on, right? It will go on, okay. But they are only asking me for the 3000 radian component, so I will only discuss about this component. So what is the peak value of this component? This is my input, right? This is my input Vin, okay. So the peak value is this. So with respect to this, I have to calculate the output. So this is the amplitude that I have to calculate. So now I can directly say magnitude of Vc will be Q into magnitude of V in, which is correct, but omega equals to omega naught, only this component, right? Only this component. So now I can directly say that it will be equals to, my magnitude of Vc will be equals to 4 Vm. Vm is how much? Currently it is peak 15 plus minus 15, right? So this will be 4 into 15 divide by pi, and this is 60 by pi, okay, into 10 of course is there, quality factor is there. So this is 600 divided by pi, okay. So what is 600 divided by pi? Almost I think somewhat 200 it will be there, right? 600 divided by pi, so it is 191 volts. So this will be your answer basically for this question. So this is a very good question and very elegant question. And if you could not understand this portion, right, don't worry, just study the signals. After that again come back to this question, you will totally understand. Because, right, there will be multiple frequency components, and for multiple frequency components the values of the impedance also will change, because resistor is frequency independent but L and C are frequency dependent. But they are not asking me about any other frequency, they are just asking me for the 5000 radian per second. So if I just care about the 5000 radian per second, so I will solve for the 5000 radian per second, and that's it. That's it, right? I will not care about the other frequency components. I will not care about this. Okay, I hope it is clear. So yeah, that's it basically for this lecture, and that's it basically for resonance, one of the most important topic, and we have discussed all types of questions. And trust me, whatever you have learned, right, you have learned the best content. Trust me, just believe me for once, you have learned the best contents, and we have discussed the most difficult questions. So now the gate PYQs will be a cakewalk for you. It will not be very difficult. Okay, so from in the next lecture we will start with a new chapter. It will be network theorems in AC networks. because you have studied network theorems in DC networks, but we will try to apply the same in AC networks. Just a slight variation will be there, except that everything will be same only. So I hope you have enjoyed this lecture. If you did, make sure to hit the like button and comment down below which part you enjoyed the most. I will meet you in the next lecture. Until then, happy learning.